So now let's take an example problem and use the equations and the concept that we have developed for Newton's method for an unconstrained multiple variable problem. Okay. So let's say if this is the function that I want to minimize, right, and the intent is to minimize this function, which is given by this equation here, how do I use Newton's method? Okay. So what we need to do is, first of all, we need to initialize, and we need to first create an initial starting point. And let's say by random number generation process, that initial starting point x vector x0 came out to be 10, 10. And again, it's a random, but for this, it doesn't matter if the values are different, the steps will follow the same. Okay. So let's assume that starting point is this. Then what we do? So first thing, similar to steepest descent method, we compute the gradient. With that information is needed. So if I take this equation and if we take the derivative of this equation with respect to x1, right, we will have 16x1 plus 4x2. If I take the derivative of this equation with respect to x2, then we will have 4x1 plus 10x2, and that gives me the derivative information of this function. Okay. But as I said, there is more information needed in the Newton's method, and we also need to have the Hessian information or the curvature information. So we are also computing del square del fx. And so we are using the equation that I described for the Hessian in the previous slide. And so I take this and basically take the derivative of that vector with x1 and x2. So that is listed here, 16 and 4. Take this, take the derivative of that with x2 and so on, and that's how we'll arrive at this Hessian matrix. Okay, so you can follow the derivation of the Hessian matrix in the last slide, and you will see that we will arrive at this matrix, which is essentially the Hessian of this function that we have. Now, since we have this two information, we can club this two information together to essentially find out the iterative scheme that is used in the Newton's method. So again, what is the iterative scheme? Xk plus 1 is equal to xk minus h inverse delta fx k. Okay, so let's see, if we instantiate k equal to 0, then we will have an equation which is x1 is equal to x0 minus h inverse delta fx, and this is equal to 0, right? So that is what we want to use. So let's use that and then see how the calculations turn out, right? So this is what we have written, and that's what, if we substitute k equal to 0, right, that is what we'll get on the right hand side. And again, I just for continuity, I want to write that k equal to 0. So this is the first iteration. Okay. So what was our x0? That was 10, 10. What was Hessian? That was 16, 4, 4, 10. We need to take an inverse of it. Remember, Hessian inverse. So this is why we have inverse. And then we need to have the gradient function evaluated at 10, 10. So whatever was the gradient function, which was essentially this function right here, which is 16x1 plus 4x2, 4x1 plus 10x2, and x1 equal to 10, x2 equal to 10. That is what going to be substituted here to evaluate the delta fx at x0, which is 10, 10, and that is what is going to be listed here. So that's what you see is clubbed here. Okay. So now we get there. So from there, we can go on. What we will do is we'll take this, we'll take the inverse of this, and the inverse of that will come out to be 1 by 44, and this matrix. And then if you simplify this, this is 160 plus 40, so 200, 40 plus 100, that's 140, and we now club this, and we can further simplify this equation. And if you multiply all this together, this comes out to be 10, 10, 2. So the resultant x1 is 0, 0. So what we have done, so from the initial solution, which essentially was x0 equal to 10, 10, using the Newton's approach in the first iteration, what we have done, we have come to a solution which is x1, and this solution is essentially 0, 0. Okay. Now we can take the second iteration and we can move to x2 if our stopping criteria is not satisfied, and we don't know what these elements are, but we can use this sort of iterative scheme, and we can also solve for x2. Okay. And again, you can check that fx1 is going to be less than fx2 or not, right? So you can do that. And the two of the key things that you need to remember, that in the Newton's method, alpha is kept 1, right? The step size is fixed as 1, and we do not play with other step size values. That's the Newton's method approach that is typically used. And then, what you're doing is also you are using the Hessian information, which is not there in the gradient descent approach. So these are the two key differences from the gradient descent approach that we have talked about. Okay. So again, how do we stop it? We can do this iterative. We can move from x0 to x1 and x2. How do we stop it? The stopping criteria could be similar. Okay. And one of the criteria that we have been discussing here is essentially this one. And again, remember, since this is a multiple variable problem, right? This equation has to be in the vector format. So this has to be a vector. And we take absolute values of the vector. If that absolute value is less than the threshold, let's say 10 to the power minus 3 or 10 to the power minus 6, whichever we choose, then we stop the algorithm. Okay. If not, then we keep on finding out the next iterative value. So that's how we move from x0, x1, x2, so on until all this stopping criteria is there. One thing that I want to mention that in the previous lecture, we developed a couple of stopping criteria. One for the golden section approach, which was based on uncertainty interval. One for the Newton method, which was based on this criteria. But these two are not only the stopping criteria. There are other stopping criteria that have been used in optimization literature, and I will ask you to, or encourage you to look into, some other stopping criteria that are useful. Okay, so even though we are saying this, and typically this is most widely used, but there are other stopping criteria that are also used in place of this, and they have their own values. So you can use them in place of this stopping criteria, but the algorithm, which is the steepest descent or the Newton's algorithm, is not going to change. When you run it, you do the iterative scheme and see whether you're satisfying the stopping criteria or not. And then based upon that, you need to decide whether you want to move on to the next iteration or whether you want to stop the iterative process. So with that, I think we have covered some very vital and important concept which is very, very widely used in machine learning algorithm. And again, I just for the sake of completeness, I delved into the Newton's approach, which is using also the Hessian information on top of the gradient information. But typically in machine learning, the most widely used algorithm is the steepest descent method, and that works well for a large class of problems. So if you just conceptually understand the steepest descent algorithm, that will be setting you up really well for understanding the deep learning type of approaches, which is using stochastic gradient methods, which are a slightly different variation on what we have discussed in the steepest descent approach. So with that, what we will do is we will now start going and discussing approaches that could be used to solve for constrained optimization problem, and we will move from unconstrained to a constrained optimization problem, and we will directly go into multiple variable, because now we have developed concepts related to multiple variable in unconstrained, and we will essentially go and develop concepts with respect to multiple variable but the constrained optimization problem. With that, thank you, and you will come back with more lectures on constrained optimization problem.